Today we're going to take a look at multiplying two binomials. And just like when we were multiplying monomials and when we multiplied a monomial by a polynomial, we can use the area model to find the product of two binomials. We can also apply the distributive property to find the product of two binomials. Let's take a look at multiplying binomials using the area model first. We're going to do things a little differently in this example. In case you haven't noticed, I haven't given us a t-shape and we have no factors in this example. We're going to do things in the reverse. I've given you an area, I've given you a rectangle, so I've given you the product. I want you to tell me which factors would have multiplied to give us this area. So we're going to determine which binomials would have multiplied to give us this product. Let's take a look at the vertical length and the horizontal width of this rectangle. We have to consider the dimensions of our tiles. The area of this rectangle is y squared, I'll write this down, y squared plus 5y tiles plus 6 ones, so 6. The vertical length is made from the y squared tile, which we know is y long, and 3 y tiles. Each are 1 wide. So with 3 of them, that would mean y plus 3 is the length of our rectangle. Now the width of our rectangle is y, because the y squared tile is y wide, so y, and we have 2 y tiles, each 1 wide, so plus 2. Using the area model, we have determined that y plus 3 multiplied by y plus 2 is equal to y squared plus 5y plus 6. Let's try another similar example. Again, I've given you the product and I want you to tell me which binomials would have multiplied to give us this product, the area. And the area in this example, as you can see, is 1 plus 3x tiles plus 2x squared. Take a look at the vertical length and the horizontal width. We have a 1 tile, which is 1 long, and an x tile, which we know is x long. 1 plus x would be the vertical length of our rectangle. Now the width, we have a 1 tile, which we know is 1 wide, and we have 2 x tiles, each x wide, plus 2x. The binomials that would have given this product were 1 plus x multiplied by 1 plus 2x, which equals 1 plus 3x plus 2x squared. Let's use the area model now to find the product of these two binomials. We have x plus 1 multiplied by y plus 3. Looking at the vertical length and the horizontal width, we can determine which tiles would fill this area. The tile that would fill x long and y wide, what tile is that? You guessed it, that's your xy tile. Underneath, 1 long, y wide, that would be a y tile. Over to the side here, x long and 1 wide, you've got an x tile here, and 3 x tiles would fill in this area. Underneath, you would have a 1 tile that would fill this area, another 1 tile, and your last 1 tile would fill in the area of this rectangle. So, x plus 1 multiplied by y plus 3 is equal to xy plus y plus 3x plus 3. And here we have it in a little fancier representation of the area model, that x plus 1 multiplied by y plus 3 gave us xy plus y plus 3x plus 3. Now why don't you try this example on your own? Grab a piece of paper and copy this down. I want you to use the area model to find the product. Once you've found the area, give the equation that relates the area to its length and its width. Pause the video and take your time. So based on the length and the width of this example, you've determined your binomials to be negative y plus 2 and y plus 3. So what tiles filled this area? The tile that's y long and y wide is a y squared tile. With that said, consider that this is a negative y tile and this is a positive y tile. That means this guy's a negative y squared tile. Underneath, 1 long, y wide. That's your y tile. And again, another y tile below. Up above, y long, 1 wide. You have a y tile. However, again, this was a negative y tile and a positive 1 tile. A negative times a positive is a negative y tile. I'm going to write that little negative symbol in there so we don't forget. Another negative y tile and another negative y tile. Down below, 1 wide and 1 long, those are our ones tiles, and we had 3 of those that would fill this here area. 3 more would fill the area below, and there we have our rectangle. Did you come up with that area? Let's take a look at the equation that would be formed by this example. Negative y plus 2 multiplied by y plus 3 was equal to negative y squared plus 2y subtract 3y plus 6. Do you notice anything about this equation? Do you notice that 2y and negative 3y are like terms? We can combine those terms. Negative y plus 2 multiplied by y plus 3 is equal to negative y squared, 2 positives and 3 negatives. That's a negative y tile plus 6. Don't worry if you didn't remember to simplify your expression. This is still new to us. We're going to get lots more practice with this in class. Here is the example again with algebra tiles. Negative y plus 2 multiplied by y plus 3 gave us the area of negative y squared plus 2y subtract 3y plus 6. Don't forget, a positive and a negative make 0. So this positive y made 0 with this negative y. This positive y made 0 with this negative y. And that's why when we wrote the equation for this example, the negative y plus 2 multiplied by y plus 3 was equal to negative y squared subtract y plus 6. When we want to multiply binomials without using algebra tiles and the area model, we are going to apply the distributive property just like when we multiplied a monomial by a polynomial. This time, however, we are going to apply the distributive property twice. Let's take a look with this example, x plus 5 multiplied by x subtract 2. The x in the first binomial has to be multiplied by both of the terms in the second binomial. So the x has to be multiplied by x, and the x has to be multiplied by the negative 2. X times x is x squared. X times negative 2 is negative 2x. The 5 in the first binomial also has to be multiplied by both of the terms in the second binomial. So the 5 has to be multiplied by the x, and it has to be multiplied by the negative 2. 5 times x is positive 5x, and 5 times negative 2 is negative 10. Take a quick look at this expression. Did you notice that two of the terms in this expression can be combined because they're like? The negative 2x and the 5x are like terms. They have the same literal coefficient. So x squared, negative 2 and positive 5. Positive 3x, subtract 10. So we can say that x plus 5 multiplied by x subtract 2 is equal to x squared plus 3x subtract 10. Let's apply the distributive property in another example. 4x plus 2 multiplied by 2x plus 1. The first term in this first binomial has to be applied to both of the terms in the second binomial. So 4x has to be multiplied by 2x, and it has to be multiplied by 1. 4x times 2x. Multiply the numerical coefficients and the literal coefficients. So 4 times 2 is 8. X times x is x squared. 4x times 1, anything times 1 is just itself. So 4x times 1 is 4x. Now let's move to the second term in that first binomial, the 2. 2 must also be multiplied by both terms in the second binomial. 2 times 2x and 2 times 1. 2 times 2x is 4x. And 2 times 1 is 2. Take a look at this expression. Are there any like terms? There sure are. 4x and 4x are like terms because they have the same literal coefficient. So if we combine these like terms, we can simplify this expression and we get x squared, 8x squared plus 8x plus 2. We'll try one more example using the distributive property. This example is a little trickier than the first two, but I'm going to talk you through with some hints. 3x has to be multiplied by both of the terms in the second binomial. Y also has to be multiplied by both of the terms in the second binomial. Let's start with the 3x. We have to multiply 3x by x squared. Let's start with the numerical coefficients. 3 has to be multiplied by what is the assumed numerical coefficient in front of the x squared? Well, you have 1 x squared, so it is a 1. 3 times 1 is 3. X times x squared. What is the assumed exponent on that x? It's also a 1. X to the 1 times x squared. Keep your base the same, add your exponents, x cubed. 3x times y squared. What is the numerical coefficient in front of the y squared? You have 1, so it's a 1. 3 times 1 is 3. X times y squared. They're not like, so we cannot keep the base the same and add the exponents. We simply combine them. X, y squared. So there, we've multiplied 3x by both of the terms in the second binomial. Let's move to the y. Y multiplied by x squared. What is the assumed numerical coefficient in front of the y? We have 1, so it's 1. 1 times 1 is 1. We don't really need to write a 1 in front of the terms, so we'll just leave that. Y times x squared. We can't keep the base the same and add the exponents with our laws of exponents, so we combine them. Y times x squared is yx squared. And y times y squared. 1 times 1 is 1. We don't typically write the 1 for a numerical coefficient. Y times y squared. Keep the base the same. Add your exponents. That's y cubed. Do we have any like terms here? Look closely for this one. The 2 in the center look like they could be the same, but they're not the same. So we have the simplified expression for this multiplication. If this one was tricky for you, don't worry, we're going to get more practice in class. So here's what I want you to do. For your entrance slip for tomorrow, create an equation to find the product of two binomials. You can use the area model or you can solve symbolically using the distributive property. If you're feeling really ambitious tonight, you can do both.